Check it out now, y'all.
nanoHUB-U Online Instruction.
Hi, my name is Edwin Garcia. I'm a professor of materials engineering at Purdue University, and I will be hosting the set of lectures in the nanoHUB called the Material Science of Batteries. This is our first lecture, and well, let me start talking about what we will be learning today. First, I want to start by defining the very basic concept of what a rechargeable battery is like. So you can think of this little block as a material that will store energy, right? And that one, you can think of it as a crystal that has that stores a species, some abstract species S, in a lattice that we are going to call A. Okay, this lattice, we're going to refer to it as an anode, and for that we're going to put that negative sign. When we are putting or taking material out of that anode, okay, we will transfer that species into the cathode, which in this case we will refer to it as arbitrarily having a positive sign. Okay, this species S will go from in order to make it a battery, we will transfer it from the red phase to the blue phase through some intervening medium. This will occur through some reaction, some general reaction, where the species, where the phase will exude the material S, Z of those atoms out of the host lattice A, and that will happen through some intervening medium, some electrolyte that will allow you to actually diffuse that material from A to C. Okay, that material, those Z atoms, will allow us to effectively use the material. And here we have the complementary reaction, where the S atoms of the S species will react with the host lattice C to form a compound S of Z of that material. Okay, this will by itself, even though there are no electrons, no charge associated with it, has actually been used to store charge, to store energy and actually there are companies that take advantage of this, because sometimes this reaction, as you go from one side to the other one, takes energy or releases energy. Okay, and you can even use that, and there are some thermal materials that what they do is they melt some salt during the day, and during the night, or even during the same day, they take that energy out of the salt in order to convert it into actual, say, motion of some vaporized liquid to move a turbine. Now, what makes this a battery is when during that same reaction, okay, we actually manage to move for every ion, for every atom of the species S, which in this case we're not really meaning sulfur, we're just meaning some general species S. We move it not through the electrolyte but outside to power our electronics or whatever device, and put it back on the counter electrode. Okay, as this happens, really what we really mean to say is that species is ionized with a positive charge, okay, and that's why we have that species transporting here through the electrolyte, okay, and releases Z electrons for every Z of the ionic species, right? And if you think about it, you want to make a good battery, you want to have this number Z, you want to make it as large as possible, okay? In the cathode side, you have, of course, the complementary reaction, okay, and you have those Z ions reacting also with those Z electrons that didn't go through the metal, okay, but instead went through the load, okay, and we put them back into the hosting lattice. This would, most of the batteries do this. If you want to make it rechargeable, typically what you do is you force the reaction in the opposite direction. Basically, you rip the electrons out, put them back in here, forcing the reaction in the opposite direction, making the ions diffuse back and react with the species in the anode. Okay, and if we do this many times, hopefully in a reversible way, then we will have a rechargeable battery. As you can see, it not only depends on what material we pick here, in both the anode and the cathode, but also depends on what material we pick in the middle. And that material has its own separate properties. Okay, that intervening electrolyte. For example, we expect that electrolyte should dissolve that species S. If it doesn't dissolve it, then we will never be able to move it from the anode into the cathode and back. Okay, it has to have, if you think about it, a high degree of solubility. Okay, it has to have high diffusivity, because even if it dissolves it, if it takes a long time to go from the anode to the cathode, that will limit how much charge we could actually move. Okay, basically the electrons will move through the load into the cathode, and will just be there sitting, waiting for the ions to react, and well, that could completely decrease the energetics of our battery. We expect to have high ionic conductivity. Why? Because as these ions are moving through between the cathode and the anode, okay, they will impose a voltage drop in that region, and that voltage drop could be detrimental to our battery performance. In fact, you can think of that layer that you want to make it as thin as possible to maximize its diffusivity, okay, and to maximize its total electrical conductivity, total electrical conductance, so that it spends as small time as possible in that region. And of course, if the solubility is small, then you also want to make it thin so it doesn't spend too much time lingering in that medium. Okay, you want it to be electronically insulating, because as we noted in the previous slide, you don't want the electrons to go through. You want them instead to go through the resistive load, so that you can actually have those as useful ions. Ideally, you would always want that to be perfectly insulating. In practice, we know that even if we just simply store a battery, if we just wait, say, a few months, the electrons will find a way through and go to the other side. Okay, and well, those are the basic requirements. And one more thing, it should be stable in the presence of both electrodes. Okay, in the sense that if you take your electrode material and you dip it in the electrolyte, you don't want, ideally, your electrode to be dissolving in the electrolyte. Okay, and you also don't want that if you put both electrodes in front of each other with the electrolyte in between, having such a large voltage difference between them could induce a reaction of that electrolyte. You don't want that either, because that degradation will lead to all these additional properties to be lost. That's certainly something that will be detrimental to the performance of the cell. Okay, so those are the basic requirements. I will talk about this later on. But right now we're going to be focusing on the electrode materials themselves, right, and to understand what are their basic properties. Okay, so one of the most fundamental properties that one always wants to extract from a battery is the material potential, the voltage, or the electrostatic, the galvanostatic drop that it has. And this axis tells you what that potential should be, okay, in volts, okay, or in joules per coulomb if you prefer. Okay, this dashed line is referred to what reference? Because when you measure the voltage, you're always measuring with respect to something, okay, that is the ground. And in material science, when you refer to that ground itself actually is a material too. So usually when that voltage is specified with respect to some specific material. If this were a lithium-ion battery, in some cases, well, in most cases, is referred to with respect to a pure lithium source. In other cases, it could be referred to, say, a hydrogen reference. Okay, so for the anode potential, this is a reaction, and if you forget for a second that we're getting electrons and ions out of this transformation requires some free energy to transform. That free energy, delta G, is related to the voltage, just to a first approximation, via the valence of that ion times F. F is referred to as the Faraday constant. which is effectively the number of electrons in a mole of charge, okay? Now, that corresponds to a voltage with respect to that reference, okay? Similarly for the cathode, okay, we also have its own reaction. That reaction will have associated a free energy very similar to the one we had before. And in every case, if you really want to use that battery, you want to always refer it again to the same reference, okay? And if you wanted to use both materials, the anode and the cathode, for a battery application, if you think about it, it really doesn't matter what the voltage is with respect to the reference in both cases. Okay, that of course does matter to have it with respect to it in order to compare them. Why? Because the voltage of the battery actually happens to be the voltage difference between the cathode and the anode. Okay, and if you want to make a battery, obviously you want to have that voltage to be as tall as possible. For the cathode and the anode, you want it to be as low as possible, because at the end of the day, you want this potential to be as large as possible. Okay, that's what's giving you the energy per charge. And electrons will naturally flow, and here we have to remember that electrons have a negative sign, so when you multiply that charge by the voltage, that will give you a negative energy that will want to go from one negative energy to an even lower energy state. So the larger this difference, the more the electrons will want to go to that potential. Okay, that doesn't mean it's going to take a short amount of time, but the driving force for that transformation will be imposed from here. Okay? Okay, now these are examples of some reactions as reported by this paper that I have here at the bottom. For example, for here you have graphite, lithiated graphite. That, as we were discussing very generally in the previous slides, it dissociates in this case into just carbon with X lithium ions that are ripped out of the graphite lattice, and for every positive ion that we take, we get one negative electron, so we have X Li plus Xe. Okay, and that reaction with respect to a hydrogen reference gives me a value of minus 2.9 volts. Okay, this you can think of it as being a very negative voltage with respect to hydrogen. If we use a lithium cobalt oxide as the cathode, you can see here that we take X of those ions plus X of those electrons, or we want to put them in. Okay, and as we put those lithium and ion and an electron inside the lithium cobalt oxide, that completes the lattice, and with respect to the hydrogen reference, we have 1.2 volts. The overall reaction can be thought of a lithiated graphite. We take that lithium out and we put it in lithium cobalt oxide, and as a result of that, we have the lithiated graphite and lithiated cobalt oxide, and the voltage of that battery, of that cathode and anode pair, would be the voltage difference between the anode and the cathode. So basically we would have to say 1.2 volts minus 2.9 volts, which happens to be 1.2 plus 2.9, which adds up to 4.1 volts, which is typically the voltage that you would expect in that kind of battery. This type of battery is typically used for high energy density applications because of the amount of energy that you can use, while others, depending on what chemistry you use, will be used for high power density applications. Now, this is another example. This is a metal hydride nickel system. Same idea, but you can see you get the same type of reactions in both cases. Okay, and here you have the metal hydride. When you put an OH radical, basically you rip out the hydrogen, leaving the metal alone, and a water molecule and an electron. With respect to the hydrogen reference, you get minus 0.83 volts. Okay, for the cathode side, you have this hydroxide, nickel hydroxide with water. It gains more hydrogen, okay, and gives away an OH radical. Okay, the overall reaction is such that the metal hydride and the nickel hydroxide combine to give you the metal with the hydride in it, and this nickel hydride giving you a voltage of 0.49 minus 0.83 equal to the 1.32 volts. Okay, as you can see here, it already feels much more appealing to have a lithium-ion battery than a nickel hydride battery. Why? Because here I have a 1.3.2 volts versus roughly 4 times what a lithium-ion battery can give you. So you can see here already that why people were moving from one type of chemistry to the other one, just from that energetics per unit charge point of view. Here's another battery. This one is we've heard about this one too. This is in the past. This is the lead acid battery, and you can see very similar reaction. In this case, the lead atom basically get this SOF4 releasing, and this is what I find very interesting. This one actually released 2 electrons. In this case, we have a Z value of 2 as compared to before, which in both cases we have a Z of 1, giving us in principle for every single molecule pair for the reaction, we get 2 charges, 2 electrons out, which in principle should give us more power, right? And in the cathode side, you can see that the SO4 radical combines with hydrogen and the electron, giving us this PVSO4 with water reaction. The overall reaction is such, as you can see it down here, and we have 2 volts when we take the difference of both reactions. Okay, there are advantages and disadvantages of all 3 chemistries. Here's one more, just to complete it. This is a redox flow reaction where you have a vanadium that basically gets further ionized, giving away 1 electron. While in the other case, we provide a hydrogen with that electron, making the vanadium oxides become give a +2 excited state plus water. So, and the Viol reaction is such that we get 1.26 volts. Okay, just to complete it, the sodium sulfur reaction has the same idea, and even though the numbers are not known, the voltage, you can see you have a voltage that deliver, depending on where you are, somewhere between 2.08 and 1.78 volts, giving you an idea on how to start thinking about these reactions and what to do with them. Okay, now, how do we determine the battery voltage overall? The battery voltage is really not just one number, it's actually a function of the local state of charge of the system. Here you have for a voltage for the lithium manganese oxide system as a function of how much lithium we have put in it. Okay, this is all with respect to a lithium reference. So you can see on this side, basically we have Mn2O4 on this side, while over here, when Y equals 1, we have a fully lithiated LiMn2O4 system. Down here, the voltage drops roughly to a value of 3, and actually there is another lithiated phase that can also be used as a battery, okay, and this is LiMnO2, okay, but the reaction between the LiMn2O4 and LiMnO2 are such that this transformation could be non-reversible and induces a lot of stresses, so people typically focus either in this phase or in the low voltage phase. For the high voltage phase, if you think about it, the advantage is that we have a larger potential, okay, and for the low voltage phase, what we may have is a plateau that makes it more stable. Overall, when one lithiates from having no charge to taking in all the charge, from say fully charged to fully discharged cell, what happens is that in some cases, some regions in the battery will actually cross this phase transformation, and as one keeps using the battery, eventually we have all these little clusters of irreversible material that we cannot use. My point here is that the voltage as a function of amount of lithium does change, although to a first approximation you can think of it as having a value of 4. You know, out here is roughly 4.1, down here is roughly 4, okay, and there's a little wiggle in between that. There's a reason, there's a scientific reason for that, and we will talk about that in future lectures, right? But ideally we would like to always have that curve in the material. For the anode we have something very similar. Okay, in this case, this is a graphite reference. Remember that voltage that we were talking about. In this case, with respect to lithium, the voltage when X is close to 1, in this case x is around 0.6, we get basically fractions, we get millivolts of response, okay? And as we are taking away lithium, the voltage starts to increase. And in some cases it can go up as high, at least it has been reported in some cases can be as high as 12 volts. And the voltage that we would get out of a battery would be the difference between the cathode and the anode, okay? And just to make the picture a little bit more complicated, when you discharge your battery, the cathode goes from here to here, and the anode goes from here to here. In other words, the cathode goes from left to right, and the anode goes from right to left. Okay, the voltage in the anode with respect to the pure lithium reference increases, while the voltage in the in the cathode with respect to the pure reference region decreases. Okay, it is that difference that one that gives you the voltage. Clearly, the largest voltage you will get will be when you have a fully charged system. And even if you take the charge out very slowly out of that battery, eventually you will lose, how much is this? 1.2 volts. And I think there should be a 1.2 over here, simply by reaching the fully discharged process, even if you end up never making it to a y equals 1. In this slide, you can see the difference between both of them. So what determines the potential of the cell, just like we did it graphically a few slides ago, it is the difference between this voltage subtracted with this voltage as it comes up, the one that gives us the overall potential. You can see here in a dashed line the potential of the entire cell. Okay, so as we go from left to right in the cathode during discharge, we go from right to left, inducing this additional voltage drop in this very last part, this very end of the discharge sequence, forcing the voltage to drop to a value below 2 volts. What exact shape that curve, that dash curve will get will depend on the properties of the electrolyte. Here you have the electrolyte with different salt concentrations. And you can see here 1.1 moles per decimeter cube, 1.2, 1.4. Each of that amount of salt that you put into the electrolyte will change the conductivity, will change its diffusivity, how much you can actually dissolve in it, how much lithium you can dissolve in it. Okay, and the name of the game is to pick what material you're going to pick as your cathode to make this curve as flat as possible, and what material you're going to pick as your anode to maximize how much charge you're going to put in it and to minimize this drop that occurs at the end. Okay? In future lectures, we will talk about that selection from the pure material selection point of view, and we will also introduce concepts like the language that people use in the material science community and the batteries community to describe the systems. See you next time.